Welcome to our presentation on Specification and Diagnostic Tests. Our aim today is to delve into how we ensure the reliability and robustness of our econometric models. As the insightful statistician George Box once stated, all models are wrong, but some are useful. This powerful quote perfectly encapsulates our objective: to equip you with the knowledge and tools, specifically within EViews 1314, to build models that fall into that useful category. We'll be focusing on critical diagnostic checks that prevent our models from leading to unreliable predictions and potentially costly, misguided decisions. Understanding these tests is paramount to extracting credible insights from your data. When we violate a core assumption of a regression model, like heteroskedasticity, it triggers a chain reaction, much like a series of falling dominoes. The first domino is the violated assumption itself. This immediately leads to the second, biased standard errors. While your coefficient estimates might still be unbiased, the crucial measure of their uncertainty becomes incorrect. Consequently, the t-statistics and p-values, which rely on these standard errors, become invalid, meaning you can no longer trust them for hypothesis testing. The final domino to fall is your conclusion, leading to potentially false policy or business decisions. This is the ultimate risk of ignoring diagnostics. Remember, an ordinary least squares model is only considered blue, best linear unbiased estimator, if its underlying assumptions hold. Even a model with a very high R-squared, say 0.99, can be statistically invalid if its residuals contain patterns or violate other key assumptions. Diagnostics are not optional. Ignoring them leads to invalid inference, rendering your t-stats and f-stats useless. To effectively avoid the diagnostic domino effect we discussed earlier, we need a systematic approach. This diagnostic map provides a comprehensive framework for evaluating ordinary least squares, or OLS, models. We can categorize these crucial diagnostic tests into three main buckets. First, we have residual diagnostics, which examines the properties of the error term. This includes checking for issues like serial correlation, which can be detected with tests such as Breusch-Pagan-Godfrey, and heteroskedasticity, using tests like White's or Breusch-Pagan. The second category is stability diagnostics, focusing on whether the model's parameters remain constant over the entire sample period. Here, we look for structural changes using tests like CSUM. Finally, coefficient and specification diagnostics ensure the correct functional form of our model, employing tests such as Ramsey reset for nonlinearity and examining multicollinearity through VIF. By systematically working through this map, we ensure the integrity and reliability of our econometric models. When evaluating your econometric model, the first crucial step is to determine your data type, as this dictates which diagnostic tests are most relevant. If you're working with time series data, where observations have a natural order over time, your primary concern is typically serial correlation. This occurs when the error term in one period is correlated with errors from previous periods. For this, you should always begin by running a Breusch-Pagan-Godfrey LM test. Once serial correlation is addressed, consider secondary threats like structural breaks, which can be identified using tests such as CUSUM or CHOW. Conversely, if your data is cross-sectional, such as surveys collected at a single point in time, your main adversary is heteroskedasticity. This means the variance of the error term is not constant across all observations. In this scenario, your initial diagnostic step should be to run a White or Breusch-Pagan test. This decision tree provides a clear roadmap, guiding you to prioritize the most likely problems for your specific data, thereby ensuring more reliable model inference. This slide provides a practical overview of how to access various diagnostic tests within EViews. As we've learned, running these tests is crucial for ensuring model integrity. The key takeaway here, as highlighted in the EViews tip, is that almost all diagnostic tools are conveniently located under the View drop-down menu of your estimated equation object. To check for issues with the error term, such as serial correlation, which we discussed earlier with the serial correlation LM test, or heteroskedasticity, using tests like White's or Arch-LM, you'll navigate to View Residual Diagnostics. For assessing model linearity with the Ramsey reset test, checking for parameter stability with CUSUM or recursive tests, or identifying influential outliers with influence statistics, you'll find these under View Stability Diagnostics. Always remember to estimate your equation first before accessing these diagnostic options. Serial correlation, also known as autocorrelation, occurs when the error terms of a regression are correlated with each other across time. The Breusch-Pagan-Godfrey LM test is the modern standard for detecting this. The intuition is to check if the residuals can be predicted by their own past values. We achieve this by running an auxiliary regression, where the residual at time t, denoted E sub t, is regressed on its own lagged values, like E sub t minus 1, and the original independent variables. The null hypothesis, or H0, for this test is that there is no serial correlation, meaning the coefficients on the lagged residuals, like rho 1, are all 0. To interpret the result, if the p-value associated with the chi-square statistic is less than 0.05, we reject the null hypothesis. This signifies that serial correlation is present, and our model is incomplete, rendering standard OLS inference unreliable. While Durbin-Watson was an older standard detecting only first-order correlation, Breusch-Godfrey offers flexibility for higher orders. After checking for correlation and errors over time, we must also check the consistency of their variance. Let's move on to heteroskedasticity. Moving on to our second diagnostic method, let's discuss heteroskedasticity. This occurs when the variance of the error term in our regression model is not constant across all observations, which violates a key assumption called homoskedasticity. Conceptually, if you plot your residuals, homoskedasticity would show them evenly scattered around 0, forming a consistent band. In contrast, heteroskedasticity would appear as a fanning out or cone shape, indicating that the spread of errors changes with the values of your independent variables. To formally test for this, we commonly use the White test. This general test involves regressing the squared residuals on the original regressors, their squares, and their cross products. The null hypothesis for this test is homoskedasticity, meaning the variance is constant. If the p-value from the White test is less than 0.05, we reject this null, concluding that heteroskedasticity is present. While White's test is excellent for a general check, if you have reason to suspect a particular variable is driving the varying volatility, the Breusch-Pagan test might offer more targeted insights. Moving on to our third method, we address model stability and specification. Even if residuals appear well-behaved, the model's underlying structure might be incorrect or unstable. The Ramsey reset test helps us identify functional form misspecification. This means checking if we've omitted important nonlinear terms or even key variables. It works by adding powers of the dependent variable's fitted values to the regression. If these terms are statistically significant, it signals a specification error, implying our original model was incomplete. Another crucial aspect is parameter stability. The CUSUM test, or cumulative sum test, checks for structural breaks in the model's coefficients over time. This test plots the cumulative sum of recursive residuals against critical bounds. If the line crosses these bounds, it indicates a structural break, meaning the relationship between variables has fundamentally changed. For instance, like how economic relationships can shift after a major event, such as the 2008 financial crisis. Both these tests are essential for ensuring a robust and well-specified model. Our fourth diagnostic method focuses on detecting individual outliers, which are observations that can disproportionately influence our regression results. Sometimes a visual check, like this influence plot, tells the story more clearly than a p-value alone. The chart displays influence statistics, such as R-student, DFITS, and Cook's distance, which are measures of how much the regression line changes if a specific observation is dropped. As you can see, One particular observation around point 20 stands out significantly, indicating a very high influence on the model, far from the rest of the data points. This highlights a potential outlier that needs further investigation. In EViews, you can easily access these tools by going to the View menu and selecting Outlier Diagnostics from your estimated equation. To practically apply our diagnostic tests in EViews, remember this crucial workflow. You must always estimate your equation first. Diagnostic views and tests are only available after a model exists. Once you have your estimated equation object open, almost all the diagnostic tools you need are conveniently located under the View menu. For issues related to the error term, you'll navigate to View, then Residual Diagnostics. This is where you'll find key tests like the serial correlation LM test, various heteroskedasticity tests such as White, Breusch-Pagan, and Arch, as well as normality tests like Jark-Bara. This structured path ensures you can systematically evaluate your model's assumptions. This slide illustrates the configuration dialogues you'll encounter when setting up diagnostic tests in EViews, specifically for serial correlation and heteroskedasticity. When performing a serial correlation LM test, such as the Breusch-Godfrey test, EViews will prompt you to specify the lags to include. It's crucial to match this lag length to your data frequency. For instance, you typically use 4 for quarterly data. Choosing an incorrect lag length can significantly reduce the power of the test, potentially leading you to miss an existing serial correlation problem. For heteroskedasticity, the dialog shows various test types, with the White test selected. This test, as we discussed, involves regressing the squared residuals on the original regressors, their squares, and their cross products, which is reflected in the description you see here. The Include White Cross Terms option allows you to incorporate these interaction terms into the auxiliary regression. These dialogues are accessed through the View menu under Residual Diagnostics after estimating your equation, and setting them correctly is vital for reliable test results. Let's look at a practical case study involving a model of stock market volume. Our first step, as always, is to establish a baseline by running a standard ordinary least squares, or OLS, regression. At first glance, the results of this initial model appear quite impressive. We see an R-squared value of over 0.95, which suggests that our model explains more than 95% of the variation in the dependent variable. This often leads to a false sense of security. However, a critical red flag emerges when we examine the Durbin-Watson statistic, which is approximately 0.35. Recall that a Durbin-Watson value close to 2 indicates no serial correlation, while a value near 0 strongly suggests the presence of positive serial correlation. This scenario perfectly illustrates what we call the high R-squared trap. A seemingly excellent R-squared can often mask serious underlying econometric problems. Just like a car with a beautiful paint job might still have a terrible rattling noise from the engine, we can't trust this model for reliable predictions without further investigation. The low Durbin-Watson statistic is our first major clue that we need to investigate further using our diagnostic tools. Let's formally test for serial correlation using the Breusch-Godfrey test. Following our initial suspicions, we formally conduct the Breusch-Godfrey serial correlation LM test. This is a critical step for time series models. Looking at the test results, specifically the probability value for the chi-square statistic, you can see it is 0.0000. This p-value is significantly below our standard 0.05 threshold. Therefore, we unequivocally reject the null hypothesis, which states there is no serial correlation in the model's residuals. This outcome confirms that our model indeed suffers from serial correlation. This problem undermines the reliability of our standard OLS coefficient standard errors and t-statistics, making any inference from this model potentially misleading. It's a clear signal that the crime of autocorrelation has been committed. As we continue our diagnostic checks, we now confirm the presence of heteroskedasticity using the White test. Looking at the output, specifically the probability values for the F statistic and chi-square statistics, we see they are all 0.0000. This is well below our typical 0.05 significance level. Therefore, we firmly reject the null hypothesis of homoskedasticity. This means the variance of our error terms is not constant across all observations. This finding, coupled with the serial correlation we detected earlier, creates what we call double trouble. With both autocorrelation and heteroskedasticity present, the standard errors produced by OLS are biased, and consequently, our t-statistics and p-values are invalid. This renders any inference drawn from this model unsafe and unreliable for making policy or business decisions. This slide details step 3 of our diagnostic process, a stability check using the QSUM test. The cumulative sum, or QSUM, test is vital for determining if the parameters of our regression model have remained constant throughout the entire sample period. Here, we see a plot of the cumulative sum of recursive residuals, which is the blue line, against time, ranging from 1980 to 2010. The red dotted lines represent the 5% significance bounds. If the QSUM line crosses these critical bounds, it indicates that the relationship between the variables in our model has fundamentally changed at some point during the sample period. As highlighted in the graph, our blue line does indeed cross the upper red bound, specifically around the late 1990s or early 2000s, signaling that parameter instability is detected. This crossing signifies a structural break in the coefficients, meaning our model's underlying dynamics were not stable. Such a break could be due to significant economic events, a policy change, or a crisis, rendering the model unreliable for the entire period. This is crucial because if coefficients change, our interpretations and predictions based on a single model are no longer valid. When our diagnostic tests for issues like serial correlation and heteroskedasticity fail, as they did in our case study, the appropriate remedy is to use robust standard errors. Specifically, we turn to HAC standard errors, which stands for heteroskedasticity and autocorrelation consistent. The Newey-West method is a widely accepted approach for this. In EViews, we don't alter our original model specification. Instead, we re-estimate the same equation, but simply change the covariance method in the estimation options, selecting HAC Newey-West as shown in the screenshot. The crucial point here is that your original coefficient estimates will remain exactly the same. However, the standard errors are now adjusted to be robust to the diagnosed problems. This leads to new, valid t-statistics and p-values, which we can finally trust for accurate hypothesis testing. For those who prefer scripting or want to ensure reproducibility, EViews has a powerful command language. Here's a quick cheat sheet for the tests we've discussed, assuming your equation object is named EQ01. To run the Breusch-Pagan-Godfrey serial correlation LM test, you simply type EQ01.auto. For a White's heteroskedasticity test, the command is EQ01.hettest, type White. To perform a Ramsey reset test for functional form misspecification, for example with two fitted terms, you would use EQ01.reset, n equals 2. You can also display a QSUM plot for parameter stability using EQ01.QSUM. Finally, to re-estimate your equation using the AAC robust standard errors we just discussed, the command is EQ01.ls cov AAC. A pro tip for building these scripts is to first perform these actions using the graphical user interface. EViews has a capture window that records the corresponding command for every action you take. You can then copy these commands to build a script for your entire research project, making it easy to rerun and document your work. As we conclude, I want to leave you with a final thought. Diagnostic testing is not about finding a perfect model, which, as George Box said, doesn't exist. Instead, it's about ensuring your model is robust and reliable enough to support sound decision-making. This meticulous approach transforms your model into a valuable tool. To delve deeper,